Welcome to the talk about roadblocks for CSP and where to find them. Today we want to talk with you about about our most recent research that we conducted at CSP. So that I and my colleague Lea has conducted together with our colleagues Katharina, Michael, and Ben. And actually, it was planned that me and my colleague Lea will show you, well, the results of this research, where we conducted a qualitative study with 12 real-world developers to uncover the root cause behind misconfigurations of CSP. However, due to her being very sick at the moment, luckily it's not COVID, I'll try to take over her part. So sorry in advance if I'm struggling on some slides of this talk. So in this talk, I will not only present you the results of our most recent work, but we also present you some numbers and graphs from other research that we conducted at CSP in order to give better examples and supporting numbers for the finding of our most recent work. So let's get started with what the hell a CSP actually is. Well, one of the most prevalent security vulnerabilities in websites is cross-site scripting. And to perform such an attack, an attacker lures a victim's browser to execute malicious JavaScript. In the example here, you can see that the victim's browser is lured into issuing a GET request to a vulnerable service containing, and this request contains a script tag that loads a malicious script. This script tag is, due to the nature of this vulnerability, embedded in the response from the vulnerable server. Therefore, the browser will load the malicious script and execute the JavaScript code in the context of the vulnerable site in the victim's browser. So this malicious code is able to do everything legitimate code is able to do. So it has access to the session IDs, to all forms. So it is easy to steal credentials, hijack sessions. And the code is also able to perform state-changing actions in behalf of the user and do many more harm. That's where CSP kicks in to mitigate the effect of those markup injections. And it basically acts as a last line of defense against those attacks. It is basically a list of trusted JavaScript sources that are allowed to be loaded and executed by the browser. So as soon as the server has a correct CSP header in the response, the evil script is not even requested by the victim's browser. CSP was already developed in 2012. And in a snippet here, you can see that there is a script from ad.com that programmatically adds a script from company.com. And there is also an inline JavaScript present in the HTML. Back in 2012, the only possibility in CSP to allow those scripts was to add the domains to the allow list and also allow the execution of inline scripts using the unsafe inline expression. However, this would also allow an attacker to inject inline JavaScript. Therefore, in 2014, they added support for nonces to the CSP standard. And by embedding such a nonce as an attribute to a script tag, as you can see it in the code snippet here, we can now allow trusted script tags to be executed. So we can also whitelist, allow inline scripts to be executed. However, ad.com still adds company.com programmatically. Thus, we still need to allow this domain in addition to the nonce in our CSP allow list. In 2016, they then added support for the strict dynamic source expression. This expression basically automatically propagates the trust to scripts that are added programmatically if they were added from already trusted sources. And therefore, we don't need to put the company.com domain in our allow list. As you can see, the CSP standard has evolved over the course of time. But in addition to its original use case, the restriction of script content, CSP has evolved into a multi-tool for web security purposes. Nowadays, it can also restrict a plethora of other different content types, such as images, styles. It can restrict the capability of an attacker to exfiltrate the stolen data, for example, via restricting the targets of the XHR or fetch API. And CSP is also capable of controlling framing behavior and enforcing secure network connections. So let's take a look on how the adoption of CSP has increased since its release. In a previous work, we took a look at the CSP adoption of the historical top 10,000 websites. And as you can see in the red line of this graph, the overall adoption of CSP is increasing. And more than 10% of the top sites are currently deploying CSP. Also, the usage of new features of CSP in CSP level 2 and 3 is increasing. So everything looks okay-ish, right? Well, if we take a closer look at the deployed policies, only less than half of them actually deploy a CSP that tries to mitigate the effect of cross-site scripting. And even worse, the vast majority of those sites use expressions that make their policy trivially bypassable by an attacker. At the end of the aforementioned longitudinal CSP study, we also notified the users about inconsistent deployment of their framing control because many of them did not use CSP to control framing, but rather the old and deprecated XFrame options. We also asked them to complete a small survey, and here the participants believed that CSP is a viable option for them to mitigate the effect of cross-site scripting. However, most of them also confessed that their website would currently not work with a strict CSP, which actually motivated us to do our most recent work, because until now, previous research only tried to make an educated guess on why developers face certain problems with CSP. And this guess was based on data that was gathered from the website's behavior and its source code. In our recent work, however, we want to go beyond this educated guess based on technical observations. We want to understand the human as core part of that technical system, such that we can promote changes on APIs or mechanisms based on evidence and not based on assumptions. Therefore, we want to find out what are the root causes of insecure practices when deploying a CSP. What strategies do developers adopt when creating a CSP? How well do developers understand the associated threat model? And what perceptions and motivations do developers have when dealing with CSP? To get this evidence based on the human mindset and behavior, we conducted a semi-structured interview with 12 real-world web developers. And during this interview, our participants reported on their real-world problems with the content security policy. And to get more fine-grained technical insights, we also incorporated a drawing task about cross-site scripting attacks and a coding task where the participants were asked to create a CSP for a small web application. Afterwards, we transcribed the interviews and analyzed them in an open coding process. And with the resulting codebook, we were then able to find motivations, strategies, and also uncover problems that the participants had when dealing with the content security policy. But let's first focus on our drawing task. In this drawing task, the participants got a blank sheet as it is displayed on the right side. This sheet contained 4 stakeholders that might interact with one another during a cross-site scripting attack. And we then asked the participants to draw and explain the process of cross-site scripting attack of their choice, and ask then afterwards where CSP would block this attack from happening. The result of this drawing task allowed us to get a better understanding of the participants' mindset about cross-site scripting and CSP. Notably, all participants really chose to draw a server-side cross-site scripting attack, while only one participant mentioned that cross-site scripting can also be a client-side problem. So it seems that the server-side presence of the vulnerability seems to be far more prominent in the heads of our participants than the client-side version. 2 participants actively mentioned cross-site scripting as a server-side problem and concluded that CSP is therefore enforced on the server side, which not only shows a misunderstanding of the mechanism itself, but also misunderstanding of the underlying security issue. One motivation of our participants to deploy a CSP was CSP's actual use case, so the mitigation of web-based attacks. Those attacks are not only covering the original use case of CSP, so cross-site scripting mitigation, but also other use cases like TLS and enforcement, or getting fine-grained control over framing, resources, or data connections of the web application. On the other hand, there are also external motivations like penetration tests, a security training of the developers, or an incident that motivated the developers to have a look on the content security policy. One participant even reported that they also deployed CSP to act as a role model for other web companies, such that more websites are deploying a content security policy. With the help of our participants, we are able to identify a broad variety of roadblocks. I'd like to give you a brief overview of our findings, starting from the perspective of an average web developer. So CSP is a rather complex mechanism and nobody knows everything. Therefore, the developer might have knowledge gaps or misconceptions regarding CSP. But let's take a look on how complex CSP can be in practice. In a study published last year, we were able to take a look on how CSP has evolved over the course of time. And this longitudinal lens allowed us to take a closer look on the development cycle of CSP in real-world web applications. In this case, it's Airbnb's journey to a secure CSP. They started with a policy in report-only mode, and that's already good because that's the way to go. And they started in November 2014 with 17 entries in their script source. In March 2015, they then added the whole HTTPS schemata to their default and script source, while their policy is still in the report-only mode. Probably they have done this because of too many violation reports that they gathered using the report feature. In May 2015, they then switched from the report-only mode to enforcement mode However, the whole HTTPS schema was still present in the allow list. Nearly 2 years, more than 2 years and 222 changes later, in December 2017, their allow list has grown to 32 entries, while the HTTPS schemata is still one of those entries. At that point, they started to experimenting with a secure report-only policy on single days. And every time they have done those experiments, they added more domains to the policy. And in January 2018, they first tried to enforce their new policy. However, they added the HTTPS schema again after less than 1 day, probably due to some fatal errors that occurred in their app. And then finally, in March 2018, they had a second try to enforce a secure CSP, and they finally succeeded with that. So, as most of you know, Airbnb's main business is their web presence. And it is a big company, but still, they needed 3.5 years to secure a CSP. So CSP deployment is arguably very complex, even for big companies, probably because big companies have big applications. But yeah, let's get back to our average developer. And this developer, due to the knowledge gaps, might start an online search to get more information about cross-site scripting attacks and how to build a proper CSP. Or as we all do during the development process, we search for a certain error message that is displayed in, for example, the development console. However, the resources that are available online often lack a bigger picture of the underlying issue, and in worst case, the developer even finds misleading claims or receives wrong suggestions how a certain problem can be fixed, as you can see in this Stack Overflow screenshot. Another problem in the mindset of some developers is that security is built into their framework. And also some developers think that security is only something that is optional. So security is only a nice to have feature in their mind. Then at some point, the developers start working on an application, which is in worst case, an existing application with a lot of legacy code, which will then result in a massive engineering effort because all this code need to be reconstructed to be CSP compliant. Even in that small example code that you can see here, we can have multiple issues like inline scripts, inline events, or dynamically added JavaScript, such that we need to rewrite the code and propagate nonces to the programmatically added scripts, such that proper CSP can do its job. Also, our developer is not working alone, but as it is common, they work in a team at a company. However, in this company, they might have different teams working on the web presence. And those teams might not all be aware of CSP compliance. So one team might cause issues with the CSP because they are not aware of the CSP and not aware of, well, CSP compliant coding standards, as it was reported by one of our participants that where the marketing team, well, basically caused a lot of errors in the CSP. Also, the company might have contracts with, for example, certain advertisement vendors. So the developer cannot freely choose which third parties can be used in the application. But are third parties really such a problem to CSP? Well, in another study conducted by Marius Steffens, they have shown that many problems regarding the usage of insecure practices in CSP, like unsafe inline, were not caused by first-party code, but rather a problem of third parties that mandate the usage of unsafe inline in this case. They mandate it either because they are using inline scripts, which could in theory be allowed via propagating nonces to those scripts. But more severe, many third parties are using inline event handlers, which cannot be nonced and therefore require unsafe inline to be executed. Also, Stefan's data has shown that this problem is not only caused by one third party of a website, but in many cases, it's caused by multiple third parties. In some cases, even 10 or more parties are hindering the usage of a sane content security policy. And to make the problem of third-party code even worse, those parties are not a fixed set, but the exact domains of the third parties that a site includes is heavily fluctuating. In a 12-week-long experiment conducted on the Trenco top 10,000 websites, Steffens et al. Issued a crawl of those websites every week to collect the included parties for each site. Of those 10,000 websites, about 8,000 actually were dynamic pages, so pages that actually contained JavaScript. After the first week, the researchers noticed that nearly 3,000 new hosts were added, approximately half of them originating from third-party inclusions. And even at the end of this 12-week-long experiment, more than 1,500 new hosts were added, which makes a CSP, a host-based CSP, very hard to maintain. But even if all stars align and the developer can build a proper CSP, the different browser implementation and insufficient console messages and false positive violation reports caused by browser features or extensions can make the deployment harder as it need to be. For example, at the time where we conducted this study, participants complained that Safari is not supporting the strict dynamic source expression, probably due to security considerations. However, in the meanwhile, they have added the support for the expression. Also, the level of detail provided via messages in the developer console is inconsistent. Chrome is providing far more information about violations than, for example, Firefox does. But there are even more inconsistencies. For example, WebSockets are sometimes in some browsers counting into the safe self source expression, and in other browsers that the protocol does not count. Some browsers support the unsafe hashes source expressions, and some browsers do not support them, but use this behavior as default behavior. And there is inconsistent hashing of, for example, JavaScript URLs, because some hash with and some without protocol, and plenty of more inconsistencies between browsers. Also, the reporting feature of CSP can cause problems. If you, for example, gather the violation reports on a popular website with a lot of users, those users might use all kinds of browsers. In some browsers, built-in features can cause CSP violations and therefore trigger false positive violation reports. But not only the browser itself can cause violations. Also, the users might have installed all kinds of extensions and plugins that interfere with the application and cause false positive reports. Depending on the amount of visitors that the website has, it may not only lead to many false positive reports that are hindering the detection of actual problems with the CSP configuration, but one of our participants even reported a case where the amount of reports actually caused a denial of service against the own server. So one lesson that you can learn from that: don't host your reporting infrastructure on the same machine as your web presence is running. During the interview, but especially during the coding task, we have seen many different strategies how certain problems with CSP can be mitigated. For example, in the initial deployment of CSP, some of the participants start with a policy and report only mode. In this mode, the policy is not enforced, but violations are reported to the developer. Others, however, tend to start with an enforced CSP, which then results in a loss of functionality in some parts of the application. Also, tools for the initial deployment, for example, to start with a generated allow list for the CSP, were often mentioned or used during our study. Principles for CSP deployment were also presented by our participants. Some tend to use one general CSP for the whole website. Others used separate CSPs for individual pages, sometimes also deployed as HTML meta tags. Because they have done this because the requested resources for each page are different. Also, the usage of the report-only mode of CSP to get reports from the live users of the application was mentioned as a common way to find issues with the CSP. Even after the initial deployment, tools were used to maintain the CSP. For example, to analyze the amount of violation reports, for example, filtering out false positive reports. And as a third category of strategies, we have those for solving problems that occur during the deployment of CSP, which are, as we have seen in the presentation of the roadblocks, quite a lot. One big problem of the participants was the presence of inline JavaScript tags. Although some of the participants used nonces or hashes to allow the execution of the trusted inline scripts, the majority externalized the script to and then allowed self as trusted script source. But how does this look like in practice? If we have an inline JavaScript tag, we can either move its source code to an external script and allow self in our CSP, or we can add a nonce to our CSP and use the nonce to allow the execution of the script. However, the optimal solution would be to do both and enforce both using policy composition, which we will talk about later. A similar problem is the presence of inline events. However, here nonces are not an option, which is why most of the participants externalized the events and added them programmatically. Still, some of our participants used rather new features like unsafe hashes or script source attribute or the script source attribute directive to allow inline events. But let's take a look on the most common solutions here. As said, we have to add the event to the element programmatically. Thus, we have to create a script that gets a handle to the targeted element, for example, via the get element by ID function, and then programmatically add the event using the add event listener API. This code snippet does then need to be allowed in the CSP, for example, via a nonce. Again, the better option is to do this programmatic addition not in an inline script, but rather in a nonced external script. Another big problem was the presence of third-party code. Here the participants either allowed the third party as a trusted source, they self-hosted the loaded libraries, or they nonced the loaded scripts, or some even removed the dependency for the library. However, this was only possible because our small web application is, well, only a small web application. And as we have seen earlier, it is sometimes not possible to solve issues introduced by third parties. Therefore, in worst case, you need to give up a certain level of control or even allow the execution of inline resources if your third party is not CSP compliant. So, in general, if you want to deploy a CSP for a web application, the best way how you should start is deploying a CSP in the report-only mode, such that you, well, don't cause fatal errors in your application. Also, you should use a nonce-based policy if need to be with strict dynamic. Those should be preferred over host-based lists because a nonce-based CSP is easier to deploy and easier to maintain. If you start a new project, the whole application should be built with CSP in mind from the beginning, such that stuff like inline scripts and inline events are not happening. So you should thread CSP as an integral part of your development lifecycle. Also, for new applications, you should choose your third parties with care. So, if possible, only choose third parties that are CSP compliant. But if you want to add a CSP to an existing application, you should take care of the issues one after another. So, if your setup or framework supports the use of nonces, you should use nonces for all assets. Even if it is not supporting nonces directly, if you can, for example, in your backend, generate random numbers and pass them to your HTML renderer, you can basically create the nonce support yourself, and you should use nonces for all your JavaScript assets. But if for some reason, for example, a WordPress plugin is not compliant with nonces, and therefore you cannot use a nonce-based CSP, in such a case, you should allow the third parties with a full URL. And as we have seen earlier, you should move all your inline scripts and inline events to external scripts such that you can arrive at a sane CSP. But for those of you that already deployed a sane CSP, we want to encourage you to take the next step, hardening your policy. But why is this actually necessary? Many of you know from other CSP talks or blog posts that there is a plethora of ways how you can bypass a host-based list, because one of the hosts you allowed has JSONP endpoints. They might host libraries that contain script gadgets. They might be susceptible to open redirects, and so on. However, also nonce-based policies can be bypassed, can be stolen, sorry. Imagine this code snippet that you see here is hosted on a web application. If you now have an injection point right before that script tag, an attacker might inject the following character sequence. And then the double ticks at the foo attribute are consuming the actually opening script tag from the benign script. And because HTML parsers are very error tolerant, this benign JS double ticks is just seen as garbage that you can throw away. And the resulting code is then a script with a weird foo attribute that loads a script from attacker.com. But this script tag does also carry a valid nonce. So as you can see, also nonces can be stolen. So assuming you already deployed one sane CSP, either host or nonce-based, the best way to harden this CSP against the aforementioned attacks is to deploy an additional CSP. The reason why this actually works is that all deployed CSPs are enforced by the browser simultaneously. So if you have one CSP that enforces the nonces to be present on scripts, and another CSP that only allows self and advertisement.com as valid sources, a script in your application must originate from one of the trusted sources and at the same time also carry the specified nonce. And well, as in case of the initial deployment, you should always first start with the policy, in this case, the additional policy in report only mode. And then if everything is working, you should start to enforce it. So what have we seen in the last 40 minutes? Many CSPs deployed in the wild are trivially bypassable. So it seems that CSP and developers are natural enemies. However, one big roadblock for sane CSP deployment are non-compliant third parties. Also, inline codes and events, especially in big legacy applications, can cause massive engineering effort for developers. In addition to that, the inconsistent implementation and the debug messages from the browser vendors are making the developer's life harder than it needs to be. So, as you can see, there is still a lot of work to be done to make CSP the great mechanism that it ought to be. And we have not only learned something about CSP in this study, we also experienced that getting participants for usable web security research is a very challenging task. We tried to find participants via advertisements on LinkedIn. We had Twitter campaigns. We even talked with people from the OWASP Germany to share our call for participants in some Slack. I don't know whether it was the Slack of the whole OWASP or if they have an internal German OWASP Slack, but so we have tried many ways of getting participants, and we have more topics in our research area that need to be explored. So if you are interested in helping us improving the state of the web, please scan this app or visit survey.swag.cispa.saarland and, well, help us improve mechanisms like CSP. And with that, I'm happy to take your questions now in the Q&A session or later via email or Twitter.